Hello class, we're about to start 7.3 Part 1, Simplifying Square Roots. Objective 1, Square Roots of Positive Numbers. We know that some numbers can look different but have the same value, such as 1.5, which could be rewritten as 3 halves, or if we wanted to write this as a percent, we could write this as 150%. Now we have 4/6. If we rewrite 4/6 as a decimal, it'll be 0.6 with the repeat in 6, or is equal to 2/3, because we can simplify that 4/6. Negative 10 over 2 is negative 5. 35% is 35 over 100, or it could equal to, what's that, 7 over 20, or equal to 0.35. Now, this is also true of square roots. For example, find the following on your calculator. If we put in these values, we would get approximately 6.7082. And if we put in these values here, we would get approximately 0.6123. Now, simplest form of a square root. A square root is considered to be in simplified form if there are no perfect square factors inside the square root, there are no fractions inside the square root, and there are no square roots in the denominator. Okay, now we have to review the list of perfect squares. Now I took the liberty of having this already filled out because when I was trying to write it in, it would jump. So as you see here, we have 1 squared, which is 1, 2 squared is 4, and so on. Now the product property. The square root of a times b, with a and b both being under the square root, is the same as saying the square root of a times the square root of b. So let's take a for instance here. Let's say we had the square root of 25 times 4. Now if you notice, both of these are under the square root. Now, we know that this would be 100, and the square root of 100 we know is 10. But let's see if we could prove that. So the square root of 25 times the square root of 4, just like we have here in this example. The square root of 25 is 5, and the square root of 4 is 2. So it does work. It equals 10. Now we scroll down here to example 1. It says simplify the following by hand. Now the first thing we have here is the square root of 28. Now we could break 28 up. I like to break it up into the perfect squares and non-perfect squares. So I like to break it up into 2 square roots. The highest perfect square in 28 is 4. And then we would be left with 7. So when I do my radicals, in my first radical I put the perfect square root, and then the second radical I put everything that's left. Now we know the square root of 4 is 2, and we're left with the square root of 7. And this is our final answer. Now we go here to the square root of 80. With the square root of 80, the highest perfect square in 80 is 16, and we have 5 left over. The square root of 16 is 4, and we have square root 5. So this is our final answer. Next, we have the square root of 75. The highest perfect square in 75 is 25. And we will have 3 left over because 25 times 3 is 75. The square root of 25 is 5, square root 3. Now we come here to 600. The highest perfect square in 600 is 100. And we will have 6 left over. 100 times 6 is 600. Square root of 100 is 10. And then we had times the square root of 6. And that is our final answer. Now, we scroll down here. Now we're going to work with the quotient property. Now we know quotient means division. So we have the square root of a divided by b, or the square root of fraction a over b. That is the same thing as basically saying the square root of a divided by the square root of b. Now this is the same as this here. Now, if you notice with number 2, there are no fractions inside the square root. Reduce the fraction inside the radical, if possible. Then apply the quotient and product properties to break up and simplify each radical. Okay, so basically it says this. Let's say we had the square root of, let's say 10 over 20. Now, what this is stating is before we separate this and do the square root of 10 over the square root of 20, we could simplify this fraction here. 10 over 20 we know would leave us 1/2. So we have the square root of 1/2, and then we will have the square root of 1 over the square root of 2. Now, the square root of 1 we know is 1, and the square root of 2. Now, what I'm going to do, I'm going to stop it here just to show you how we broke this up. I'm going to show you in another problem how we would finish this off. But let's go here to A. We have the square root of 5 all over 36. We know 5 and 36 has nothing in common. So we would do the square root of 5 over the square root of 36. Now the square root of 5 stays the same. But we know the square root of 6 is 6. Since there is no radical in our denominator, we're done. Now we come here. We have the square root of 10 over 64. We could simplify this. 10 and 64, we could, actually 64 is a perfect square. So before we simplify this, let's do this here. We have square root of 10 all over square root of 64. Now, we will have the square root of 10 all over the square root of 64 is 4. Now, whenever you have a perfect square in your denominator, you need to go ahead and do the perfect square, even before you simplify. Now we have the square root of 15 over 27. Neither one of these are perfect squares, but we know 15 and 27 both has 3 in common, so that will leave us 5/9. Now we will have the square root of 5 all over the square root of 9. And that will leave us the square root of 5 over 3. Now, we look at number 3 here. It says no square roots in the denominator. Rationalize the denominator by multiplying by the smallest factor that will create a perfect square under the radical in the denominator. Now this is picking up where we left off with this problem. We have a square root in our denominator, which we're not supposed to have. So we would take 1 over the square root of 2, and then the lowest possible factor that would make this a perfect square is to multiply your numerator and denominator by the square root of 2. And this will leave us the square root of 2 all over the square root of 4. Now we know the square root of 4 is 2, so our final answer would be the square root of 2 all over 2. Now we're going to apply this to this next problem here. Now we look here. Our denominator is the square root of 7. Since there is no perfect squares in 7, we will multiply the numerator and denominator by the square root of 7. So we will have 4 square root 7. Square root 7 times square root 7 is the square root of 49. So this would give us 4 square root 7 all over 7. And this is our final answer. Now we go on to the next problem here, which is B. We have the square root of 2 over 5. So we could break this up. This cannot be simplified, and they don't have perfect squares. So we have the square root of 2 over the square root of 5. Now, since 5 does not have any perfect squares in it, we will multiply the numerator and denominator by the square root of 5. This will give us the square root of 10 all over the square root of 25, which is the square root of 10 all over 5. Now, just as a footnote, whenever you take a square root of a number times itself, it will end up with the original number that you had under the square root. Like the square root of 5 and the square root of 5 end up giving us 5. If we look here, the square root of 7 times the square root of 7 ended up giving us 7. So that's just a good rule for you to know. Now we go here to C. We have the negative square root of 7/12. So first of all, we really don't need to carry this negative over until we get to the end of the problem, because we know our final answer is going to be negative. So let's break this up. We will have the square root of 7 over the square root of 12. Now, before we go and multiply the numerator and denominator by the square root of 12, doesn't 12 have a perfect square in it? Yes, it does. You're right. It has 4. So we have the square root of 4 times the square root of 3. So we will have the square root of 7 over 2 times the square root of 3. Now, what we need to do is this here. We need to get rid of this radical or the square root out of the denominator. So since 3 has no perfect square in it, we'll multiply our numerator and denominator by the square root of 3. And this will give us the square root of 21 all over 2 times the square root of 9. Now we know the square root of 9 is 3. So we have the square root of 21 all over 2 times 3. Now we know 2 times 3 is 6, so it's the square root of 21 all over 6. And this is our final answer. Now we go over here to D. We have the square root of 9 over 32. Now we could break that up. We have the square root of 9, square root of 32. Now the highest first of all, the square root of 9 we know is just 3. We have the highest perfect square in 32, we know is 16. So it'll be square root of 16 times the square root of 2. So we would have 3 over the square root of 16 is 4. And we have our square root of 2. Now we need to get rid of this square root of 2, which has no perfect square in it. So we'll multiply our numerator and denominator by the square root of 2. So we will have 3 square root 2 over 4 times the square root of 4. Now we know the square root of 4 is 2. So we have 3 square root of 2 times 4 times 2. So our final answer would be 3 square root 2 all over 8. Okay, now we scroll down to the next slide here, or the next page. And we have here square roots of negative numbers. When we try the square root of a negative number, it is impossible to find a real number that works. For example, the square root of negative 25. Now, in order to make sense of the square root of a negative number, we introduce a new type of number, the imaginary numbers. Now, as you see here, we have the square root of negative 1 is equal to I, where I is called the imaginary unit. Now, if your calculator is set to the real number system, if you put in the square root of negative 25, it's going to give you an error message. So this is what we need to do. We would take this, we would break this up. 25 is the perfect square, and we had times the square root of negative 1. The square root of 25, we know is 5. Now we just learned down here that the square root of negative 1 is I. So our final answer is 5 times I, because we're dealing with the imaginary unit. Now if we were still dealing in just the real number system, our answer would have been undefined or impossible. But since we're dealing with the complex number system, or the imaginary numbers, we could actually solve a negative square root. Now it says, no, imaginary numbers were first discussed by Girolamo Cardano in 1545 and later popularized by Leonhard Euler and Carl Friedrich Gauss. And that was in 1780. The term imaginary was coined as a put down by Rene Descartes, who invented the XY axis as he did not like them. Simplify the following by hand. Now listen, we already know, first of all, that the square root of 49 is 7. And because it's negative, it's I. So it'll be 7I. Now, we have this negative on the outside of the radical, so we'll carry over the negative. The square root of 81 we know is 9. But since it's negative, it'll be 9I. Now we come here to C. Now we have negative square root of the negative 3 over 20. So what we could do is we could bring the I out front. So it'll be negative I, and then we add the square root of 3 over 20. Now we would do this like we did the previous problems when we did the fractions. So it'll be negative I square root of 3 over square root of 20. Now, 20 has a perfect square in it, which we know is 4.